so you can listen to it if you don't get the chance to finish it at the end here because of the late start. All right, so high efficiency boilers. First thing to know is that on smaller boilers under 300 MBH, the federal laws changed from the Department of Energy last year, and the new legal minimum for those size boilers, for all boilers, condensing or non-condensing, is 82% AFUE. You can't have anything less efficient than that. If you have something older in your inventory, you can sell it and install it, but they cannot manufacture anything lower than that anymore. As part of that exact same ruling, standing pilots were eliminated completely, so everything has to be some sort of electronic-based ignition, no burning gas when you don't need it type thing. And then the most important one out of that, that has been the biggest stumbling block for some of the guys who do these smaller boilers and the residential boilers, is that you have to have a means for automatic water temperature adjustment. For most of us, that means outside air reset schedule. That's built into a lot of boilers anyway, and if it's not, it's easy to get. But that's not the only way to do it. There are other mechanisms. I know the boiler down on the right-hand side in that picture, the Utica one, they're working on a method of staging their boiler, based on temperature differentials and things like that. But for the most part, it means you have to have outside air reset as part of your boiler. That's for boilers smaller than 300,000 BTUs. Larger boilers are not subject to this particular rule. We'll talk about both residential and commercial boilers today. One of the things I want you guys all to be aware of is that there's boatloads of free money sitting out there for condensing boilers from the various utilities. We got folks all over the Midwest on this call, so I put some of those up on here. I'm not going to read them all to you because that would be boring. But just look at the column that applies to your utility. So if you're in Illinois, Nicor, Peoples, and North Shore Gas are the main ones. If it's a public building in Illinois, like a fire station or school or village hall or something like that, you don't get your rebate from the gas company. You get it from DCEO, Department of Commerce and Economic Opportunity, and the dollar amounts are huge. So if you do any public sector work, you should definitely be looking at these boiler rebates. The dollar amounts are big. A 1 million BTU boiler is a $14,000 rebate. That basically buys them a boiler. You still got to pay to install it and the labor and all that, but you're basically getting a free boiler. But even the private sector ones are pretty good. For 1 million BTUs, Nicor, as you see on the bottom down there, $5,000, $4,000 for the city and North Shore. Out in Indiana, $900. Up in Wisconsin, Focus on Energy is $3,000. Missouri is just $200 across the board, regardless of the size of the boiler. So it's not very exciting over there for you guys. And Michigan's a little bit lower as well, but still fairly decent rebates. That first column across there, or excuse me, first row across there, the smaller than 300 MBH size, I listed both the residential and commercial rebates there for those ones. But all the other ones, $299 example, $399, $500, and $1 million, those are all commercial rebates there. You got a 1 million BTU boiler in a residence, we should probably have a conversation. You might not need a rebate. There are tons of other rebates available related to the boilers other than just replacing the boiler itself. A very popular one is adding an indirect hot water, domestic water storage tank onto your boiler plant, so your boiler can do both space heating and domestic water. So that's a popular rebate add-on. A couple utilities, Peoples and North Shore, are trying this year for the first time having rebates for combo boilers. We got a boiler and a tankless water heater all inside one box. Pipe installation is a common rebate, obviously programmable thermostats. On the commercial side, you'll often see rebates for adding reset controls to an existing boiler. You don't get that rebate for a new boiler because for a new boiler, you pretty much have to do it by law anyway, either residentially via the DOE rule I just talked about or commercially via the building code. But if you add outside air reset controls to an existing boiler, that's typically rebatable. And some of the utilities have rebates now for various burner control options, linkageless controls, high turn down burners, stuff like that. And pretty much everybody's got rebates for tune-ups commercially, and a few are even doing it residentially as well. If you need more information on the rebates, we have a whole 1-hour recorded webinar on that on our website if you want to learn about all the specifics for the various rebate programs. So on to condensing boilers themselves. Condensing boilers are a fairly new technology in the U.S., and by new I mean 20 years old, which for the HVAC world is fairly new. A little bit older than that in Europe and other countries, but here in the U.S., it's pretty much a 20-year-old thing here at this point. Maybe not quite 20, but 15-year-old thing. The whole main goal of a condensing boiler is to save energy and reduce your fuel bills. That's the whole reason to do it. If you don't care about your energy bills, then just keep your old boiler and be happy. But if you want to save some money, that's where the condensing boilers come into play. Condensing boilers, by definition or by default, are pretty much always 90% efficient and greater. To get something to go into the condensing mode, you're pretty much in that realm. There are some folks that may have an 88 or 89% boiler that's kind of a partially condensing boiler, but pretty much 90% and above is condensing, 85% and below is non-condensing, and anything in the middle there is just kind of an oddball, and not many manufacturers play in that arena because it's kind of hard to know if something's going to condense or not condense at 82, or excuse me, at 88%. You can combine boiler plants, old and new boilers, condensing and non-condensing, low mass and high mass. That can be done, and we'll talk a little bit about that today, so you can kind of optimize your plant as a whole. And condensing boilers do require some different installation rules. For example, you see over here on these 5 boilers we got, let me get my John Madden out here. We got 5 boilers here, 1, 2, 3, 4, and 5. And those guys all have their own individual intakes for combustion air, and they all have their own exhaust pipes as well. You can see where the old louvers were in this picture for bringing in combustion air and so forth. When you switch to these condensing boilers, pretty much for the most part, every boiler manufacturer is going to have one generally PVC intake and exhaust per boiler. So you're probably not going to be sharing anything anymore in terms of exhaust stacks. The venting is also going to be a different material, right? So the old boilers we use, like the ones in this picture, were vented in sheet metal. That's no longer going to work. Once we get to a condensing state, some of the things that precipitate out of the condensate are going to be acidic in nature, and that will eat up the sheet metal. So you can't vent it in sheet metal anymore when you switch to a condensing boiler. You pretty much have to go to stainless steel or PVC. And obviously PVC is cheaper, so you're going to want to do that whenever possible. So PVC for condensing boilers is going to be the most common venting method. So you will have to do some work on the venting when you change from an old to a new style boiler plant. You're going to have to switch from sheet metal to PVC venting, and you're probably going to have to get everybody a dedicated venting pipe. As you can see here, these 4 boilers, they're all dumping into that common plenum back there, and that's exhausting straight up. That will no longer work when you switch to the condensing boilers. The other thing that might change is, depending on the type of condensing boiler you use, you may have to do a little bit of piping work. Jerry typed in that he lost audio. Can everybody else still hear me? That way I'll know if it's on my end or his end. So if you can hear me, do me another quick favor. All right, some guys are typing in, yes, you can hear me. We'll keep going on. I'm not sure what the deal is for Jerry there. You might have to switch to low mass, primary, secondary piping with some of the low mass boilers. We'll talk about some reasons for that in a little bit here. But the basic issue there is that I need to have a reasonably high flow through a reasonably tight wound heat exchanger when I go to these low mass boilers. So like with an old cast iron boiler, for example, like the ones in this picture, you basically got, I don't know, a 2-inch pipe coming in, dumping water into this big, heat exchanger, basically this big drum, and then pulling water out. The pressure drop is very low. When you go to a low mass boiler, it's a coil, like a wound up coil style heat exchanger. So I got to push water all the way through that coil. So if I try to do that with the main pump for the whole building or the main pump for the house, it'd be a pretty big load. So we divide the workload in half, and we do half on the primary, half on the secondary. So this is what that typically looks like if you've never seen primary, secondary before. So on the left side of the drawing here, we got our primary loop, right? So that's this guy here, leaves the boiler, goes through the pump, circles around, goes back into the boiler. That pump is sized just to handle the pressure drop related of this boiler's heat exchanger, as well as the small amount of piping here in the boiler room. He doesn't give a crap about your house or your building or your campus or anything else going on in the building. That's not his problem. His job is just to circulate water through this one little loop in the boiler room, and he's sized just to make it through that loop and through that boiler's heat exchanger. The other pump, pump 2 in this drawing, his job is to shove water all the way through your radiators or your baseboard or air handlers or whatever you got, radiant floor, and his job is to do that loop, right? Now you can see there's one point here where these guys share some piping. That's this common pipe right here in the middle where we have AB on there. That's the only point in time that these 2 loops are connected. So hydraulically, it's the same thing between those 2, but the loops themselves are hydraulically separated. So if I have, oops, all right, if I have pump 1 on and pump 2 off, right, so the boiler's running, but that particular loop on pump number 2 doesn't request anything, then the water is going to go that path, right? However, when pump 2 turns on, and assuming these pumps are the same size, the water will pull out this loop and go like this and back around, and there's going to be no water flow from A to B, right? If they're not equally sized, the two pumps, then I will have some water flow. Right, so that's kind of the idea here is one pump is sized for the building, one pump is sized for the boiler, and I can pick and choose which way it goes. And as you get into more complex piping arrangements, you can have multiple secondaries and even multiple primaries. If you want to learn more about that, we have a whole class on piping and pumping that I can direct you to at the end of this presentation here. Just wanted to introduce the primary secondary piping concept for these boiler retrofits. So the reason to go to condensing boilers is to get higher efficiency. We get a lot of questions about, well, how efficient are things going to be? And how much money am I going to save? So the first thing to think about is, well, what do you have today, right? Your steel boiler or your copper boiler or your cast iron boiler, how efficient is it now? It's very common that I get an answer back, it's 80% efficient. And it very well may be, but depending on how old the boiler is and how well the boiler has been maintained, that 80% originally rated boiler 30 years ago may not be operating at 80% anymore. So as a kind of a general rule of thumb, we take a 1% deduction penalty per year of age up to 10% maximum. So if you tell me you got a 30-year-old boiler that was 80% efficient, for my calculations, I'm going to assume it was 70%, unless you give me combustion analyzer data showing me what the real efficiency was, 77, 79, 81, whatever you really measured. But the point is it's going to derate itself as the age goes on. Condensing boilers, on the other hand, they're going to be 90% and better. And a lot of them seem to be in that 93, 94% range. That's a pretty common point for most manufacturers. So 93, 94, 95, 96%. So if I go from an 80% to a 95% boiler, I'm going to save basically 15, 16% energy. If I go for something really bad, a 60%er, up to the best on the market, 98, 99%, I'm going to save 35, 40% of my energy. Additionally, if I add outside air reset controls to a system that didn't have it previously, I'm going to get another 10 to 15% savings out of it. And this kind of will help explain why that is. So what we got on this particular chart here is down on the bottom, we got inlet water temperature to the boiler. So this is my return water from 40 to 240 degrees in this particular chart. And up the left, I have boiler efficiency, and this chart goes from 80 to 100% in this case. Right, so normal boiler return water temperature is typically 160 degrees in a normal system. For whatever reason, 100 and some years ago, somebody decided all the boiler plants need to operate at 180 degrees. So we sized all the piping and radiators for 180 degrees. And we sized all the radiators for a 20 degree delta T. So 180 supply, 20 degree delta T. That means I got 160 return water. So most plants are operating at that point. So this particular boiler on this generic chart is basically an 86% efficient boiler when it's operating at those normal conditions. And that's fantastic. It's a good boiler. Everybody's happy. If I ask for some hotter water temperatures, then as you can see, my efficiency is going to decline slightly. If I ask for some cooler temperatures, my efficiency is going to go up slightly. When I get to this point here, which is approximately 130 degree return water, when I get to that point, my efficiency spikes up very dramatically, right? I get these very high efficiency percents. If I ask for 100 degree water, assuming my line is straight, I basically got a 94, 95% efficient boiler. If I say, hey, give me a 50 degree water, my 86% boiler starts operating like a 99% boiler in this example, right? Because what's happening there when I get to a cold enough return water, if my return water is cold enough, it's going to cause my flue gases to condense earlier, which means I'm going to be able to save some of that latent energy to back to my heat exchanger, and I'm going to get higher efficiency. For you guys that do furnace type work, you've seen condensing furnaces, right? I got two heat exchangers, a primary and a secondary. Condensing boilers are very similar. I typically don't have two heat exchangers. It's just one really big, long heat exchanger with lots of surface area to it. And that cold return water hitting those cooler flue gases towards the back end of the heat exchanger, they're going to condense. And it takes a lot of energy to change state of something. So to change something to condense, it takes a lot of energy. So that energy is going to come out of our flue gases, which saves the energy in the building instead of sending it up the stack, right? So the colder the return water, the better for a condensing boiler. This example here is a very similar chart. This is for a very specific boiler that we use in our training classes in our lab that we live fire. So it works very similarly. 160-degree return water here. This is a 93% efficient boiler, right? If I look at it that way, it's 93% efficient. Boom, right? And if I start dropping my return water temperature, as you can see, around 130, it spikes up. It's not quite as dramatic a spike as the other one, because this is already a high efficiency boiler, so there's only so much room to go here. But you can see it does get more efficient as I get colder. The other thing that happens is if I turn the firing rate down, I can get more efficient. So as you can see down here, the yellow is the 100% firing rate. The magenta, purple, pink color, whatever that is 2/3 firing rate. And the blue one is 1/3 firing rate. So if I just have a normal 160-degree return water, my boiler, and I turn it down to 1/3, I could pick up, say, another 2% or so efficiency. Another 2% efficiency, right? And the reason for that is that my boiler has a certain size heat exchanger, and if I reduce the firing rate, I have more surface area of heat exchanger relative to the gas I'm burning. It's kind of like you want to think about it the opposite way. Keep the gas burning consistent and triple the size of the heat exchanger. While that surface area would give me a lot more efficiency. It's kind of the same thing in reverse here. I'm going to keep the heat exchanger the same size because I can't swap out heat exchangers every 5 minutes. I'm going to reduce the firing rate. So it's kind of like having a triple oversized surface area. So I can get more surface area by turning the burner down with a modulating or stage burner, and I can get more efficiency by turning the burner down or by lowering the water temperature, or both. So the question becomes, how cold is too cold of water to send to the condensing boiler? As you might know, with regular boilers, non-condensing boilers, you'll see stickers on them that say don't let the return water get below 140 or 150 or something like that, because they don't want to get to a condensing mode very often. If they do, that acidic nature of the condensate eats up their heat exchanger. So if you want to have a condensing boiler, you have to have the heat exchanger made out of something that is resistive to that corrosion, something that's a non-ferrous metal, something without iron in it. So you can use stainless steel, you could use aluminum. Those are two very popular ones. You can use some more exotic things like copper nickel, titanium, stuff like that. But pretty much stainless steel and aluminum is what you're going to use. And then at that point, I don't care how much it condenses. In fact, I want it to condense. And the colder the water, the better. So pretty much the coldest water I could take would be something that's slightly above freezing, because I don't want to pump slush around, right? So for sake of argument, we'll say 40 degrees is the coldest return water I can get. So if I got a snow melt system and I'm sending 50, 60-degree water back to my boiler, it loves it. That boiler becomes a 99% efficient boiler. Radiant floors, loves it. If you got snow melt or radiant floors, there's no reason not to put a condensing boiler in. Even if you bought a new boiler last week and it's a cast iron one, throw it away and get a condensing boiler. The payback is going to be dramatically quick. For other systems where I don't have, snow melt type water and cold radiant floor, how do I get these water temperatures lower? Well, the thing I can realize is that I don't need 180-degree supply water every single day of the year, right? If it's a 0-degree day out, fine. I need 180-degree supply water because that was my design. But at any other point in time, I don't need 180, right? If it's 60 degrees out, I can get away with a lot cooler water. So this chart here is a typical outside air reset schedule. This particular one goes from 120 to 180-degree supply water, and it goes from 0 to 60-degree outdoor air temperature, right? So if it's 0 degrees outside, boom, 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 give me 180-degree water, or anything colder than 0 even, give me 180-degree water. If it's 60 degrees or higher outside, give me 120-degree supply water. And then I can pick anything in between. If it's 30 degrees outside today, boom, boom, give me 150. Right? If it's 10 degrees outside, boom, boom, give me, I don't know, whatever it is, 168 or whatever the number comes out to be. Right? So I got to tell my boiler two different things. I got to tell them when to start and what temperature to operate at. So 60 degrees, 120, and when to stop doing the reset, 0 and 180. And anything in between there, the boiler will figure out on its own. The vast majority of condensing boilers from most manufacturers nowadays include outside air reset control built into the boiler control itself. Now you still got to mount the outside air sensor, but everything else is already built into the boiler, right? So the outside air sensor, if you didn't already know, needs to be mounted on the north side of the building, at least for those of you that are in the northern hemisphere, which is all of the United States. You got to be on the north side of the building because the sun never shines there and you won't get any false readings. If you can't get it on the north side of the building for some reason, like it's 200 yards away from the boiler plant, like it is in our lab here in Melrose Park. But then in those cases, you need to put it where you can, but make some kind of sun shield to dampen the effects of the sun beating on that sensor and giving you false readings. If you do have a radiant floor system where you're operating with much cooler water temperatures, you can still do outside air reset. It just won't be as dramatic of a reset, right? So instead of 180 degrees on a 0 degree day, you can give me 110 degree supply water on a 0 degree day, right? And as it gets colder outside, or excuse me, warmer outside, down to up to 60 degrees, in this example, you can give me 85 degree water, right? So instead of resetting from 120 to 180, I'll reset from 85 to 110. By the way, even at 110 supply, I got 100 degrees, 95 degree return. I'm in a condensing mode. So the radiant floor, I'm in a condensing mode all the time, right? With a cast iron radiator or baseboard or air handler job, I'm only going to be in a condensing mode some of the time. But the more time I can get there, the better. And the outside air reset schedule helps me get there. You can put outside air reset controls on non-condensing boilers. It does make some sense to save energy, right? Because like we said, the cooler the water we provide, the more energy we save. However, I can't get really aggressive with the schedule because I can't let that return water drop below, say, 140. So I can kind of only do really half of this outside air reset curve here, right? I can do this part of the reset down here, but I can't do the other half of the curve, so I don't get quite as much energy savings. Adding outside air reset controls to a non-condensing boiler can be a little bit tricky and costly. I got to buy a controller, whereas with a condensing boiler, it's built into the existing controller, right? But here I got to buy a separate controller and a sensor for outside air and a supply water sensor and wire all that stuff up and possibly even a mixing valve to protect the boiler so I don't return very cold water and put all that stuff in. And now it's going to cost me $1,000, $1,500, something like that. So if I got a 5 million BTU boiler that's in good condition, it would make sense to pay to add these controls and save some energy, right? But if I have a 500,000 BTU boiler, to buy $1,500 worth of controls probably isn't going to pay itself back. So I'd probably be better off upgrading my boiler plant. Kind of how that usually goes. If you guys have questions, type them in the chat box on the bottom right-hand side, and I will do my best to answer them. Another thing we look at quite a bit, and we teach this in some of our half and full day classes if anybody comes to those. We teach right-sizing equipment. As you probably realize, most boilers are oversized out in the marketplace. And by most, I mean 100% of the boilers that we have looked at in the past 20-some years. A lot of you guys know Bill Bailey in our office. He does a lot of our boiler design work, and he helps me teach some of these classes. And pretty much every week he's going out helping people resize boilers, especially this time of year. And in whatever it's been, I don't even know, 26, 27 years. He's never once been to a job that he could not downsize the boiler. Literally 100% of the boiler plants are oversized. There's a John Hopkins study that came out a few years back saying that systems on average are oversized by 60%. On average, that means somebody's oversized like 200% and somebody else is actually correctly sized for the average to get to 60%. So these things are grossly oversized, and we'll teach you some methods of downsizing them. Obviously, you can do load calculations. That's the best thing to do. And sometimes required by law, but sometimes you can't get the data for what the building's made out of and how good the windows are and that kind of stuff. So we do some other tricks that we can teach you in class to measure some of the components in the system to figure out how much you can safely downsize a plant. Some of the benefits of downsizing it, other than just having a lower first cost, right? If I'm going to buy a 1 million BTU boiler plant or I'm going to buy 500,000 BTU boiler plant, obviously the costs are different. And if I can downsize that plant when I'm upgrading it, I can use that savings to pay for better, more efficient boilers as opposed to paying for bigger, less efficient boilers, if that makes any sense. The other thing is you're never at full load, right? It happens less than 1% of the year at like 3 a.m. in the middle of January, right, for a few hours, maybe a couple times a year. So rounding up to larger boiler sizes doesn't make any sense. Whatever the load calcs come out to, put that size boiler in. If you want to round it off, round it down. Stop rounding it up. All the safety factors you built into your load calcs, you're already oversized anyway. The more correctly sized the boiler is, the less oversized it is, the less swings we're going to have in cycling the equipment on and off. If it's oversized, it's got to fire and then turn off, fire and turn off. We get a lot of comments from people saying, well, I'm going to buy a modulating boiler, though, so if I'm oversized, it'll just ramp down. Yeah, it's going to ramp down, but it only can ramp down so far. And depending on the boiler size and manufacturer, that may be ramped down to 20%, maybe 30%, something like that. If I can only ramp down to 20% and it's a low load day, and my load is less than that, then I'm going to have to cycle on and off like I would have done with an old crappy boiler. So the modulating boiler does not save you in that regard. And then obviously if you can get your first cost down, you've probably got a better shot of winning the job. You can beat somebody else's bid. We have countless number of jobs that we do every year where we help a contractor and partner up with them. And because we've downsized the plant, our bid ends up coming in, our collective bid, our product and their installation labor ends up coming in less than the guy who didn't do that. And then, obviously that contractor gets the job. I got a comment from Russell saying, in northern Minnesota, it can get down to 60 below zero. And God bless you, Russell, for living there. So don't undersize the boiler too much. Just to be clear, to clarify for Russell and anybody else that's got a similar train of thought, I'm not telling you to undersize the boiler. That's not really my goal. My real goal is to just get you to pick the size boiler that your load calcs show you need. Right? Normally people round up. I realize I just said if you're going to round down. I'm not saying round down 5 sizes. I'm saying if your load calc comes out to say that you need 305,000 BTUs and your choice is buying a 300 or 400,000 BTU boiler, okay, get the 300. 5,000 BTUs isn't even really measurable. I'm not saying drop down to 100, but don't undersize it. Just correctly size it. That's kind of why we came up with that right sizing slogan, because we're just tired of people oversizing it. But it's a good point, Russell. I mean, you can't go too much smaller. And I know it kind of gets into some of the classes we do, but one of the ways we do it is we go around and we measure all the radiation in the building. So we literally count all the radiators, their height, width, number of sections, and so forth. If it's a radiation job, if it's a baseboard job, we measure all the fin tube and just the fins, not the whole enclosure, just the fin part. And we go to our tables and we look at that and say, okay, this radiator or baseboard or radiant floor or air handler or whatever it is can put out this many BTUs maximum. It can't put out any more. And then we add them all up for the whole building. And if it comes up to say that we got 1.3 million BTUs radiator and we got a 2 million BTU boiler plant, where am I going to shove the other 700,000 BTUs even if I wanted to? I only got 1.3 of radiator. So we want to get you to size it at least down, round it down, or resize the new plant for as big as the radiators are existing, because obviously they're covering the heat load now. And then if you do, manual J residentially or ASHRAE load calcs commercially, you can get even more aggressive with correctly sizing it. Eric asks if Illinois requires that we do manual J load calc for every new boiler installation. So the way the code's actually written for the energy code in Illinois, Eric, is that you would have to do residentially have to do a manual J load calc for any work that you're doing that's falling under the code. And installing a new boiler would be that case. However, what's happened in most municipalities is they're choosing to enforce it such that if you're doing a new construction building, new construction home, or if you're doing a major renovation, then they've been enforcing that you need to do the manual J load calcs. If you're just swapping out a like-for-like item, most municipalities have not been asking for the load calcs. They've just been, saying, okay, it's like-for-like, we're just going to let it slide, even though the code technically would require you to do the load calc. So you need to be prepared to do it. You probably should just do it anyway so you can size the boiler correctly and kind of go from there. All right, so I'm going to talk about some specific boilers and specifically compare some low mass ones to high mass ones and talk about when you would use different ones. And to do that, I'm going to illustrate different manufacturers' equipment to kind of compare those examples here. HTP is one of the manufacturers that we use quite a bit. We've been using them. Bill in our office has been using them literally since 1999 when they first started making boilers in the U.S. Prior to that, they only made water heaters, but now they make both. And they were really one of the first guys to have condensing boilers in the North American marketplace. Everything else prior to that was made in Europe and sometimes imported over. But the United States finally got on the bandwagon, 12, 15 years ago, whatever it was. So that first one there where it says 1999, that's actually what we call the Munchkin boiler. Some of you guys may have seen those in the field. Some of you guys love them. Some of you guys hate them. The reasons you hate them are probably because they're the first ones that were here and misinstalled very frequently. Like people didn't do the primary, secondary piping and then wondered why the boiler didn't run very well. So things like that. But once everybody got educated up to speed, those boilers became very reliable. In 2006, they came out with a little wall-hung version called the Contender. 2007, the bigger commercial sizes, which now go up to 1.7 million BTUs. And then in 2009, they retired the Munchkin and brought out the Elite line to get a little more efficient and to enhance some of the things that people didn't like about the Munchkin one. So those are low mass boilers, and this is a typical piping schematic for low mass boiler plant. So let's see if I can kind of highlight it here. So down here at the bottom is my boiler, right? So his primary piping is this red line that comes on out of here. My primary loop goes through my pump number 1 and back to the boiler, right? So that pump number 1, P1, his job in life is just to circulate water around this loop all day long. He doesn't care about anything else. That's all he does. That's his job. These other guys here, oops, I did that same thing again. These other guys here, there's 3 pumps up on top. Each one of them is for a dedicated zone. So this first one here, he's doing this radiant floor and coming back to the return, and his return is here, and then he gets his new water through that same loop, right? This guy going to an air handler or whatever, he's doing the same thing, and that last radiant zone is doing the same thing, right? They're just circulating these loops here. They don't care what happens down here in this loop. That's not their problem at all, right? So each one of these guys has their own dedicated arena to work with. Circulate this top loop or circulate these bottom loops. Pump number 1 is controlled by the boiler. He decides when pump 1 shuts on and off. And he provides water through this primary loop. Everybody else grabs water as they need it. So for example, if pump 1 is moving 10 gallons of water, great. And let's say for sake of argument, these other 3 pumps are 4 gallons each, just for sake of argument, so 12 gallons total. If pump 1's on and this first radiant zone turns on, great. 4 gallons go up to that top loop. And then the other would be 6 gallons of P1 just circulate back through, right, across this crossover bridge here. These closely spaced T's, these are 2 T fittings. Put as physically close as you can get them. If you can physically connect them to each other, all the better. Kind of the rule of thumb is you don't want to be any more than like 3 to 5 pipe diameters away from each other. So if you got 2-inch pipe, these 2 T's should be no more than 10 inches apart, right? That's kind of the rule of thumb. There's other ways to do it other than the closely spaced T's. You can use those Taco twin T's. You could use like a Calafi hydraulic separator. You can use a boiler buddy. There's different ways to do it, but the closely spaced T is the least expensive way to get your dedicated primary and secondary loop. And in this example, we have 3 secondaries. The other thing that you see in this drawing is that we have an indirect domestic tank, kind of like I talked about for the rebates for the utilities. I already got this boiler running. I can use that boiler to heat my domestic water if I want as well. So an indirect tank basically looks like a water heater. It's typically a vertical tank, well insulated. There's 3 major things different. 1, there is no burner on the bottom of this guy, right? Instead of a burner on the bottom, we have a hydronic coil in here. And he's just getting hot water from the boiler, running it through the coil, and returning it back. That water in the coil never touches the domestic water in the tank. It's physically separated, obviously. And the third thing that's different is there's no flue pipe up the top of this water heater. Most water heaters lose their heat up this giant flue pipe that's run right up the middle of them. If I get rid of that flue pipe, close that off with insulation, and I get rid of the burner on the bottom where air was coming in and close that off with insulation, there's really nowhere for the heat to go, right? So these guys only lose, like, say for sake of argument, half a degree every hour of temperature, right? It's that good of a type tank. So what happens when there's this domestic water sensor in here, and let's say I want to maintain, 160 degree water. If the water temperature gets below that, that signal is going back to the boiler control. He says, well, you asked for 160 degree water, Ryan, but I see you only got 150. Maybe it's time to heat the domestic water. The boiler will tell pump number 1 to shut off, and then he'll tell pump number 2 to turn on. And then now my main loop looks like this guy here. Oops, looks like this guy here. Right, through pump 2, through this coil, and then return back to the boiler. Right, and all my water just going right from the boiler into this coil, heating up the domestic water. Once that sensor says, hey, I'm happy, I'm satisfied, he sends a signal back to the boiler, says, I'm all good, thank you very much for the hot water, and now I can turn pump number 1 back on and start heating my building. If I stop heating your radiant floors for 10 minutes to heat your domestic tank, no one's going to know. I mean, you can stop heating for 2 hours and no one's going to know. There's so much mass in the radiant floor. But even baseboard and radiators and stuff, if I stop using them for 10 minutes, they'll still be hot and people will still be getting heat that's residual while I heat your domestic tank up. So it's a fantastic way to save some energy here. Dan types in a question asking, what about double wall heat exchangers for domestic? I'm assuming your question, Dan, is really when am I required to do that? So generally speaking, we try not to use double wall heat exchangers for domestic water. The reason being is a double wall basically is a heat exchanger inside a heat exchanger. So in between there's an air pocket. If you guys do insulation work, you know that an air pocket's a fantastic insulator. So double wall heat exchanger reduces the amount of heat transfer I can get between my my boiler water and my domestic water, right? These guys right here. So I don't want to use double wall heat exchanger unless I really need to. And there's a few municipalities that will require you to do that. City of Chicago being the most famous of them, obviously. So if you're doing a City of Chicago job, you're going to have to put a double wall heat exchanger in. You won't get quite as good heat transfer, which means you have to run your boiler a little bit more to get the transfer. But it's still way, way, way more efficient than a 50%, 60% efficient standard water heater. If you're in a municipality that doesn't require that, you don't have to do it. It's kind of an overkill thing anyway, because there's so many checks and balances involved that I don't know. It doesn't really seem necessary to have double wall unless you're required to by code. This is a common tank that we use. This is an HTP one. We also use ones made by Utica. We use ones made by Niles Steel Tank and some other groups as well, just depending on the size and type that we need. We tend to use a lot of stainless steel tanks. We can get glass ones that are less expensive, but typically the stainless steel ones have a lifetime warranty. So we typically go that route, for a few $100 more, just make it a lifetime and be done with it. And 120 gallons is a pretty normal maximum size for residential, and then beyond that we would get commercial tanks if you needed 500 or 1,000 gallons or something like that. And then above 1,000 gallons, it's kind of hard to even get it in the building, so we typically would just bank 1,000-gallon tanks together. So some of the specific boilers we would be looking at, this particular one is an HTP Contender. Now it's called the MC series. They renamed it. It's a low mass boiler, so it requires primary, secondary. This guy's a wall hung, typically 93% efficient or so, depending on the exact size of it. Sizes go from 50 to 120. It's fully condensing, right? So that means I got to have the PVC venting, Schedule 40 PVC venting. I got to have a condensate drain, somewhere to put this condensate down. And some municipalities will require you to have a condensation neutralization kit, which is nothing more than a PVC pipe with a bunch of limestone in it. But you may be required to do that. Typically on our bids, we put that in there, and if you don't want it, let us know. But we typically include it, assuming you're going to need it. And by the way, when we bid a job with one of you guys, we put everything in there, right? So we put the pump in there, we put the strainer in there, we put the neutralizer kit, the concentric vent termination kits. We put it all in there because you're probably going to need all that stuff. If you don't want it, that's fine. Let us know. We'll take it off our quote. We put it all in there so you know what you need, and then when you compare us against somebody else, you kind of see the price difference. We get a lot of calls saying, "Oh, yeah, you're $500 high." We're like, well, does your other bid have these other things? No. Well, once you add them in, you realize it's actually we're low. But in any case, that's kind of how that goes. This is a fully modulating boiler. This particular one has a 3-to-1 turn down, which means it goes from 33% up to 100% firing rate. It's not a very good turn down, but this is an entry-level boiler here. It's Benson Schedule 40 PVC, 2-inch. And most residential boilers have a 10 or 12-year warranty. The HTP ones all have 12-year, limited on the heat exchanger, 3-year on the blower, 1 year on the parts. So Kevin asks, he types in if that's a residential or a commercial warranty on there. That is the residential warranty on there. I'll show you some commercial ones in a minute. The very small boilers, right? Even the 120,000 BTU one is only 84 pounds, so one guy can mount it on the wall. That's typical setup. Sometimes they're so light. Sometimes we build them in a panel type setup and then ship them somewhere. So the primary loop is literally just this loop right here, where my red dot is. That's it. That's the primary loop. Over here, in this case, they have a Claffey. Actually, they have a Taco hydraulic separator, but really it's just the, it could be two closely spaced T's like we talked about before. So there's my primary loop. I have two secondary loops with these two pumps here, right? So one supplies out that way, returns back around, and does his thing like that. And then his buddy next to him does the exact same thing, right? So it's pretty easy to do the primary, secondary. It's not prohibitive. You just got to do a little rework in the piping in the boiler room. The big brother to that Contender is the Elite boiler. These guys go from 55,000 BTUs up to 399. By the way, you'll see a lot of boilers that are at 299, 399 type sizes. That's because at 300 and 400 they go into different category ratings for different reasons, right? So at 300 it becomes a commercial boiler as far as HRI is concerned, so it has to get rated commercially. 299 is still a residential boiler, regardless of the kind of building you install it in. And then usually at 400, some other rules kick in with the fire marshals and things like that. So you'll see a lot of 199, 299, 399 sizes for that reason. Smaller boilers, 299 and less, are rated in AFUE, annual fuel utilization efficiency. Larger boilers from all manufacturers, 300,000 BTUs and up, are rated in thermal efficiency. So those two are not interchangeable, but they're fairly close, within 1% or so. This one has a 5-to-1 turn down, which means it can modulate from 20 to 100%. Has the same heat exchanger as that little one I just showed you. It's a stainless steel low mass heat exchanger, and it's got a pretty beefy exhaust fan, so it can vent up to about 200 feet, which should cover you for most situations. One nice thing about HTP boilers, whether it's the little one I just showed you, this one, or some of the bigger ones I'll show you in a minute, they all have the exact same circuit board in them, exact same control. So it's literally one replacement circuit board for, like, I don't even know at this point, 40-some different boiler lines. So it's very easy to deal with that. And that controller does a couple things standard out of the box. It can automatically sequence 8 boilers. So here I got 2 boilers on my screen. I can connect them with a data cable and tell this guy he's number 1, tell this guy he's number 2, and then the number 1 will decide when to run each one. So maybe he'll be the lead boiler for a couple days, then the other one will be the lead boiler for a couple days, then number 3 will get a few days, number 4 will get a few days. If the lead boiler can't keep up, he'll decide when to bring another boiler on. He'll decide if it's more efficient to run 3 boilers at 60% efficient versus 2 boilers at 100, or whatever the math comes out to. So all that's built in. You just literally connect them with a cable and say you're number 1, you're number 2, you're number 3, etc. It has domestic hot water built into it, which is what I was showing you there with the tank. You just got to add the domestic sensor into that tank so we can know what the water temperature is out there. So that's pretty common stuff. These guys obviously get a little bit bigger. They weigh a little bit more. There's the 4 smaller ones. Those guys all vent in 3-inch PVC, and the bigger ones vent in 4-inch PVC, and they get up to 250 pounds for 399,000 BTU. So you can wall mount that, but that's pretty heavy to mount on a wall. So we tend to stop mounting them on the wall when we get to about 200,000 BTUs, unless you got a really well-made wall. So we can't wall mount them like that picture shows there, but that's got a diamonds, steel-plated wall, so that's a little different. And the big brother in that series, and then we'll move on to some other stuff here, is the ModCon. It's modulating condensing boiler. It used to be 300, 500, and 850,000 BTUs. You could stack them like it shows in the picture over there. And now for the 1 million and 1.7 million BTU sizes, you can get them pre-stacked at the factory with a pre-manufactured manifolding kit and a manifolding kit for the PVC side as well. So you only got one vent going up. I believe it's an 8-inch vent. So you can get 1.7 million BTUs, one boiler, but internally it's really 2 boilers stacked together. It's got some redundancy there. Same exact heat exchanger, same exact controls. It's low mass. You still do the primary, secondary. Because it is a commercial product, you'll see the warranty down there. It says it's a 10-year warranty instead of 12. For whatever reason, that's pretty common with the boiler manufacturers, but it's still 3-year blower and 1 year on the parts. So that's the big guy there. There's a job that we did, or there's actually half of a job that we did. You can't see in this picture, but to the left of these boilers, there's another 8 boilers, all modular on there. This was a condo building replacement we did with a contractor probably about 3 years ago. Got a pretty decent rebate from People's Gas. I believe it was $51,000 or $53,000 rebate, which was nice. There's also some boilers that do domestic water on this same building. Same boilers we used, just piped them up to the domestic plant instead. But you can fit a lot of stuff in a small space. The reason we went this way on this job, other than the rebates, was that all these boilers were up in the penthouse of a 20-some story building, and these boilers fit nicely up the elevator. They're all about, 3 feet high, 2 feet wide, and they just get a little bit deeper as you get to the bigger sizes. So they fit up a typical elevator very nicely. Sometimes we also use them to directly feed domestic water. So instead of doing the indirect tank like I talked about before, if we do an apartment building like this one is on the left over here, we might just have the boilers run domestic water right through the boiler heat exchanger and into the tank. That we don't have the penalty loss for the double wall heat exchanger or single wall heat exchanger for that matter. But the one thing it does is reduce the warranty if you use straight city water instead of recycled boiler water. So instead of a 10-year, you get a 5-year warranty, which is still better than a typical boiler, copper boiler that you might use for domestic. And then the right over here is actually a swimming pool job. I believe this one is the Kalahari Water Park in Wisconsin, I believe. We didn't do that job, but our neighbors to the north did. They sent us the picture because it's a pretty cool job. But you can run chlorinated water directly through these ModCon boilers as well without a heat exchanger. That does help your efficiency by not having a heat exchanger, but it reduces your warranty, so you're down to a 3-year warranty on the boiler heat exchanger if you run chlorine through it instead of the typical 10-year. But once again, it's still better than a typical copper pool boiler that you might use, which probably has a 1-year warranty. So one of the other things that we can do with a low mass boiler, if we want to get away from that primary secondary piping change, right? On new construction, no big deal, or new install, no big deal. But if I'm doing like a residential change out of an old cast iron boiler, maybe I don't want to put a second pump in and have to wire power to it and change the piping around. Maybe I just want to take one boiler out, put the other boiler in, and not have to do any electrical, extra work there. That's where this SSC boiler comes in. It's still a stainless steel heat exchanger, low mass. So the heat exchanger still needs the primary secondary. However, the primary loop is actually built into the boiler. So it's actually kind of a cool thing that they've done, right? So I don't have a blow up of it, but this is my heat exchanger here, and I'm an awesome artist, by the way, right? Down here, I actually have a pump built into the boiler. So my primary loop is right here. Boom. So the heat exchanger still needs the primary secondary, but I'm covered. I got the primary loop there, right? And then I got my secondary, coming out here, and I got my regular house pump doing his thing. Boom, boom, boom. Damn, that's a good drawing. I'm good. So we do that quite a bit. It's pretty flexible that way. And this guy's got a pretty nice warranty, 15-year. And Utica makes the Carrier and Bryant residential boilers for us as well. So 3 boilers fall into this scenario that we sell anyway, Bryant, Carrier, and Utica. They go from 50 up to 200,000 MBH, and the best one is 95%. And there's a few that are a little bit less than that. Still get the 5-to-1 turn down, still got the built-in outside air reset, all that kind of stuff. When we get to a little more commercial stuff, if we want to build the piping package into the boiler, we are starting to lean towards using this GB162 from Buderus. A lot of you guys probably have heard of Buderus. They've been around forever, European manufacturer, been doing condensing stuff for 20-some years. So it's a well-established product line. This particular one is the smaller sizes. They make a 290 and a 333,000 BTU. And by the way, when we talk about these MBHs and BTUs, that's input on these boilers. So when we come back to that, that right sizing thing, sometimes you take out whatever 100,000 BTU boiler, you want to put 100,000 in condensing. Well, the 100,000 old one that was 80% efficient really only had 80,000 output. Now you put in 95%, I got 95,000 output. So I've inadvertently oversized it if I pick the same size condensing boiler as non-condensing when I change it out. So all the more reason to right size it and round down a little bit there. But the nice thing about this one is you can get the piping packages built into this guy as well. It's an optional thing. And you can even get piping packages for multiple boilers getting together. So this one here has 4, I believe, 333,000 BTU on here. So that's, 1.4 million BTUs, all manifolded together from this factory kit on the bottom here, pumping built in. And it's all fitting in, 44 by 39 inches. So it's pretty tight to get it all in there. So you can get it with or without the pumping built in. Just gives you some blow up of what some of that looks like. They're Grundfos pumps, which are pretty commonly used European pumps. We use them here at TEC for 10+ years. Good pump. And that just kind of shows you the modularity of it. That's 2 boilers side by side with 2 more of them right behind it. It says here theoretically you can install them a half hour per boiler. It's probably not going to be that way on your first job, but by the time you get to the 3rd or 4th one and you crank through these things, it's pretty easy. We got a whole video on how you set it up, but they manifold together pretty nicely. If you don't want to do back-to-back and you want to put them on the wall, there's kits for doing that way as well. Some of these pictures are showing it with the stainless steel venting, but nowadays on the newer ones we use PVC venting, like that example there, right? So there's 3 of them with a manifolded kit, another 3 manifolded kit, all with PVC venting on them. Right? There's even more. So there's 3 with 3 behind them. So there's 12 of them banked together, taking up less floor space than the old plant that used to be there. Right? There's another example, same kind of thing. There's 8 of them banked together, taking up less floor space. Dan's asking if you need to flush these out each year. If so, do you have a supply valve kit? In general, our recommendation, Dan, on all boiler plants, old or new, condensing or non, is that we do not flush the water out of the system. Right? There's multiple reasons for that, but the main reason is if I flush all the water out of the system, which logically in your head thinks, oh great, I'm getting rid of some old dirty water and putting in new fresh water. Well, unfortunately, new fresh water has two problems with it. It has new minerals in it, right, which I've already precipitated out somewhere else, probably caught them in the strainer or whatever, and it has new air bubbles in it, right, because there's oxygen in water, right, and I've already bled all that air out with my air separators and my venting, so I don't want to bring new water in. A boiler plant is best served when it keeps the old same water circulating around it for 20 years, right? We don't want to bring any new water in if we don't have to. Sure, we're going to have a make-up water connection on the boiler plant if we happen to lose water or something like that, but generally speaking, we don't want to bring new water in. We want to keep all the old boiler. Dan's clarifying his question, saying he means just the boiler, and the answer to that is no also. So these are low-mass boilers, so they just have a coiled-up heat exchanger in them. So like those, like a 200,000 BTU boiler may only have 2 gallons of water in it, and it's moving through there at a fairly high velocity, so that water's not sitting in there. Now, we do have to do some stuff to clean the boiler, but most of what we do is going to be on the air side, the combustion side. We will have to open up that burner, take it out. All the boilers we're talking about so far have been water tube boilers. So water's in the tube, flames going around the tube. But take that burner out and clean in between all of those tubes to get any debris and stuff out of there, right? Vacuum it out, clean it up. On the water side, pretty much the only thing we do, Dan, is that on all the boilers we do anyway at TEC, we put a strainer on the return water side. So that strainer can catch all the debris that might be in the water, whatever it is. If got a little flux in the pipe from when we connected it up originally or whatever it is, let that strainer collect all that crap, and then we'll blow the strainer out, right? So instead of having to clean the water out of the boiler. The water's only going to be there briefly. It's not like an old cast iron or even a newer aluminum block boiler where the water can sit down at the bottom and debris can accumulate. This is all inside a tube, so it moves pretty quickly through there. So strainer on the water side, clean that out, and then clean out the combustion air side pretty good. And usually we use like those little what do you call them? Little green like kitchen like you use for your cleaning your dishes. Those little green pads. I forget what they're called. Scotch pads, I think they are. Right, we usually use those to clean the air side of the heat exchanger. They're just more modular pictures there. I won't bore you guys with all that stuff, but just know that there's lots of ways we can install these things in lots of weird spaces. One of the other things we do is sometimes we will recommend that you do not use a low mass boiler. Sometimes there's reasons to do that. There's usually two reasons. One is on a small residential plant where you got 100, 150,000 BTUs boiler or something like that, and you don't want to change all the piping around and add the second pipe. We might recommend using a high mass, high efficiency boiler. There's several different types of that, and I'll show you 2 or 3 of them right now. So I can get away from having to do the primary and secondary piping. Still get high efficiency, still get condensating boiler, still modulating, still good turn down, etc. Still outside air reset controls, all that stuff. This particular one is one style we use from HTP. If I can get this, I need to move along. There we go. There's what the inside of that guy looks like. So let's get my John Madden thing going here. Right, so in this case, instead of having the water in the tube and the flame around it, we have the flame in the tube and water surrounding it. So this is basically a condensing boiler right here, bolted to the side of a 55-gallon drum. That's probably the best way that I can describe it, although I'm sure the manufacturer has a sexier way, right? So I got my combustion air coming into this guy, right? I'm burning that through my high-efficiency burner. It's going up to this guy here, and then it's coiling down through all these loops, right? And then somewhere down here, boom, I let it go out and exhaust out my PVC vent out of the building. Right? So that's how that guy's looking. And then all the water is coming in here, filling up in the tank and going out. Actually, it's coming in the bottom and going out the top. Right? But there's very low pressure drop on the water side. I basically got a 2-inch pipe coming in and a 2-inch pipe coming out. It's a big open drum in the middle. So the low pressure drop means I don't have to do the primary, secondary piping. I still got to do the PVC venting, so there's still a little bit of work for me to do. But at least I don't have to change the piping arrangement around. So we use it in those scenarios where we want to do a direct replacement of a small cast iron boiler. And we also use it for these people, how do we usually tell you, these people that have what we call the microzones, right? They got their McMansion out there, 10,000 square feet, and they want like 50 zones, right? Some of these are little tiny zones. They want 2,000 BTU zone for their powder room, bathroom floor with its own thermostat. Well, every time that thermostat calls for heat, my burner kicks on my low mass boiler, which is not ideal. If I use one of these high mass boilers instead and I turn on that pump and pull 2,000 BTUs out of this tank, no one's even going to know I pulled 2,000 out. My burner is not even going to have to fire. I pull 2,000 out of the 55-gallon drum, life goes on. When I get enough people calling for heat, then I'm going to have to fire my burner. So it reduces the short cycling quite a bit. Kevin's asking if I can explain a little bit more on the difference between low mass and high mass. So one thing is everything in hydronics, if you didn't already know, whatever it is, we call it that because we're really lazy with the names, right? An air separator separates air, an expansion tank allows expansion. Well, low mass means I have literally low mass of heat exchanger surface area, right? And high mass means I have a lot of mass. So a low mass boiler is typically going to be a water coil with a burner shooting down the middle of the coil. For most manufacturers, that's what it's going to be. It's only going to hold a couple gallons of water versus like an old cast iron boiler, which is just going to be a big giant drum made out of cast iron that's just, whatever, I don't know, 40 gallons of water in it, right? Or a steel boiler with tubes in it. So it's literally a function of how much water, per BTU that this boiler is going to hold. And the low mass ones, because the water is moving through there so quickly, and the burner is so large relative to the mass of the water, we have to use that primary, secondary. Plus the pumping pressure drop kind of dictates we need two separate pumps. Whereas with the high mass ones, I can get away with just one piping loop. So as this example shows you here, instead of having two pumps on here and a closely spaced tees right there, I don't have that. I just got water goes out the pump, comes back in. Now this one happens to have 3 zones, but most places just have 1 zone on these small boilers. But I don't have to have that primary, secondary piping in the middle there. All right. There's other ways we do some of these higher mass ones. This one from Utica, Bryant, and Carrier, they're aluminum block heat exchangers. So they're basically designed to mimic a cast iron block, but they're made out of aluminum, which can handle the condensate. Other than that, it looks just like a cast iron boiler. Right? They hold the same amount of water the old boiler used to hold, which is a fairly high mass, hence they don't need to have the primary, secondary piping. These particular ones are only 90% AFUE, and they're just on-off. They do not modulate. But there are other ones that do modulate, which would be this guy here, the UB95, which is their big brother. They'll have full modulation, 90 to 93% efficient. The only bad thing about him is he only comes in one size, 200,000 BTUs. So we can only use it on certain jobs because of that. One thing to keep in mind with some of these aluminum boilers, though, is that they can be very particular on what kind of glycol they can use. If you're just doing a commercial building or a house or something like that, no big deal. But if you're doing a snow melt system or something, you're going to add glycol, we tend to not recommend you use aluminum. We tend to stick with the steel boilers, stainless steel boilers in those cases. Here's another aluminum boiler from Buderus. When we get to some of the bigger sizes, we kind of leave the Utica stuff and go over to Buderus. So you get up to 1 million BTUs on those guys. Aluminum heat exchanger, high mass, 92, 93% efficient typically. And then there's also some of the high mass, higher end Buderus boilers that go up to 4.2 million BTUs of input, and they're in the 95 to 97% efficiency range. They're not aluminum like those little ones were. Little ones meaning this 1 million BTU one. They are stainless steel fire tubes. So fire tube means the flame is in the tube, like this drawing down here is showing you, and water is surrounding the tubes, right? So that's kind of the difference there. So fire tube means the flame is in the tube and water surrounds it. Water tube means the water's inside the tubes of the heat exchanger and the flame is blowing past the tubes. So that's kind of the difference there. But because the water is surrounding it, there's a larger mass of water, hence the high mass boiler name, and hence not having the need for the primary, secondary to reduce the short cycling and things like that. And then there's also a cast iron version of that if you're not into the high efficiency stuff. And Utica guys have all their cast iron stuff that we do as well. Sometimes people like that for direct replacement, but we generally try to recommend people use condensing boilers when it physically makes sense for the application because you're going to save the energy to go with it. All right, so kind of the last thing I want to touch on, and then we'll wrap things up here, is we help people lay out plants all the time, literally every day. We go out and help you measure radiators and resize things and come up with a plan. But sometimes you present that plan to the building owner and they look at it and they say, $600,000? Are you serious? We haven't planned for that, right? They don't have the capital to do it. So they say, just how much just to replace the boiler that died last week, and let's just do that. And you're like, okay, that's $80,000. Great, we'll do that. Well, we don't really want to do that, right? Because that's just going to encourage people to, keep having low efficiency stuff forever. We'd rather they save energy. We'd rather they have a better product. We'd rather they get the rebate from the utility and all that stuff. So what we usually do in those cases, we recommend you mix it, right? So if my one boiler died, let's say I had 3 boilers here on this drawing, and one of them died, right? Instead of replacing him with another 80% inefficient boiler, how about I replace him with a condensing boiler? And in fact, I'm going to probably even downsize him because, once again, my plant was probably oversized. So I took the 500,000 BTU boiler out. I put this 250,000 BTU boiler in, and he's going to do most of my work most of my days. In fact, sometimes on jobs, we find that he does everything himself and the other boilers never kick on. So the key is that he has to get the return water first. So return water is coming this way, right? It goes into my boiler. He heats it up as much as he needs to heat it up to whatever the set point is, right? And if that is good enough, it can flow right on to the other, out to the plant and out to the system. If it's not good enough, then number 2 boiler has to kick on, the old inefficient guy, and help me heat it up. And on really extreme days when it's minus 10 out, number 3 can kick on and help me out as well. Well, in most of these cases, I can get 70 to 80% of my run hours on this little pony boiler that's 92, 93, 95% efficient, and I hardly ever have to turn the old boilers on. The other nice thing about these condensing boilers is some of the ones we use have what we call the dinosaur switch on them. And if he can't keep up with the load and make the set point, he closes the wiring to the dinosaur switch, which goes ahead and wires over there, and he's the go signal for the old boiler to turn on and help out. So that kind of makes the cost shock a little better for people, and they're more likely to actually replace or upgrade part of their plant than just replace it with an old efficient boiler. There's lots of ways to mix and match it. Here's a couple other drawings. These are from our friends over at Bornquist. Some ideas on how you can pipe it. So like this guy here on the top, once again, the key is as long as the condensing boilers see the return water first, I'm in good shape. Because the coldest return water, the more efficient I am. It goes through 1, 2, or 3 of the boilers, however many it needs, and the water comes back up. If the temperature sensor says that's good and I'm warm enough, send it right out to the system. But if it's not, and I didn't make my water set point yet, fine. Come down here and run it through one of these other boilers, or 2 of them, or 3 of them, however many it takes to get me up to my set point. So that's a pretty easy way to do it. Depending on the kind of control you have, you may choose to pipe it like the bottom drawing, right? Once again, though, the key is I got to fire these guys first, the condensing ones. They get the chance to heat the water first with 1, 2, or 3 of them, however many it needs. If it's warm enough, great, life is good. If not, fine, kick on another one of these other old boilers on those extreme days. What you find is that you almost never need all the boilers, right? And then when you do need a backup one, it's only going to be for certain times a year for a certain amount of hours, and get most of the run hours on the condensing boilers. Tula is asking if we have a side-by-side performance comparison summary for different boiler types. For different boiler manufacturers, probably yes, Tula, but for different types, no, because I could have a low mass that's 90% and a high mass that's 95%, or vice versa. So it's really specific on the manufacturer. It's not just a function of whether it's low mass or high mass. It's mainly a function of how big is my burner relative to the surface area of my heat exchanger. So for different manufacturers, it'll end up being a little bit different answer. And then finally, here's one more way you might want to pipe this. This also comes from our friends over at Bornquist, who supplies our B&G pumps to us and a few other things. So return water is coming in. Once again, the key is return water has to go to the condensing boilers first. If this one guy is able to keep up with the load himself based on that temperature sensor, great. Water goes out to the system, everybody's happy. If boiler number 2 has to fire, fine, boiler number 2 fires. And then if for some reason that's still not enough capacity and the dinosaur switch turns on and says, give me some more, well, when this guy's pump turns on for dinosaur number 1, that water will be pulled this way. Maybe I should do it like this. That water will be pulled this way through these 2 guys. And instead of going up that pipe there, he'll just turn himself down and go through one or both of these guys and out to the system. And here's my system pumps over there. So that's kind of nice doing it this way because now I don't have to pay the pressure drop penalty of these pumps. Like this first way I showed you, I got to pay for one of these pumps to run even when the boiler's not running. So this is not the most ideal way to do it, even though it's the easiest way to add a pony boiler. But one of these methods like this or like this would be nice. This is kind of a unique way to do it. I'm not sure who specifically came up with this piping diagram over there, but we tend to like that one over here now. We've been trying to pipe some jobs this way and it works out pretty good. I don't have to pay for this pressure drop down here. If I don't need it, go right out. We do tons of other stuff here at TEC that I won't bore you with right now, but tons of other radiant things we do with different pumps that we use. Grundfos, B&G, Relo. We make modular boiler plants in a box and ship them to your job site. Right? We can do stuff like that. We do water heaters. We do geo for some of our hydronic stuff. All the expansion tanks and air separators and all that kind of stuff. We do convectors, unit heaters, etc. We even got wood burning boilers if you want one. We've never sold one here in Chicago yet, but if you want one, we'll be happy to hook you up with it. We do tons of training, right? At TEC, we do like 160 classroom trainings a year plus 50 some webinars. Here on the screen here are some training classes that are still remaining on the schedule for the fall. We generally start the hydronic classes in late August, and a bunch of them go through late August and September. So a lot of them are already over, but there are several more of them left. Starting with next week, there's one-day hydronic basics classes that our friends from RC Sales are helping us with. They're a local rep. Then on October 9th is our typical annual hydronic system fundamentals class that Bill Bailey and I teach. That one does have PDH hours, so if you're an engineer and you need 8 PDHs, come on by. That's a good class. And we got classes specific to certain brands. I think we've done all the Utica ones for the year, but we still got the HTP boiler, has one more service class left on the schedule. And then we got some condensing boiler generic service classes that we're doing for the utility companies, gas utilities that ask us to do that every year. And all those can be found, whether they're our classes or the utility ones. You can register for all of them on our website, tecmungo.com/training, or click on training. Russell actually asked me some information about the wood firing boilers, and honestly, I don't know anything about them, but I will get Mike in our office, who does deal with them a little bit, to reach out to you, Russell, and help you with some of that stuff. Explain whether you can install them inside or outside and so forth. I know they're high-efficiency ones, though. They're gasification ones, so they reburn some of their flue gases intentionally to get a little bit higher efficiency. But I don't know, high-efficiency wood might mean like 75%. I don't know. But I'll get you some information on that, Russell. And then lastly, we do have hydronic piping software that we use that's free of charge. The Taco guys offer it, as do the Multi-Aqua. You can get it right from the Multi-Aqua website down there. And if you want to learn how to use it, you can go onto our website and look at the webinar from last month that we recorded. Maybe it's 3 weeks ago. And that'll give you an idea how that works. All right. Anybody else have any final questions they want to send in? I will do my best to answer them. Once again, I apologize for starting 10 minutes late on you guys. That was my fault. I was not able to get things running on my end. But most of you guys stayed on and waited for me. If you have any further questions, you can give me a call or an email, and I'll try to answer them. And then, Russ, I'll get you the wood burning questions answered as well. All right. Thanks, guys. Appreciate your time.